migrating monoliths to microservices based on the analysis of database access requests. Author is Sungbin Ma, Zhongwen Lu, and Chun-Chieh Li, and I am Chun-Chieh Li. We are from National Taiwan Ocean University. And this is our outline. First, I will talk about the research motivation and purpose, and then the background knowledge. And after that, I will discuss the design of the Miata system, and then the experiments and the cases, and final is our conclusions. First is our research motivation. There are two main issues in microservice field. One is it's hard to extract microservice with a single logical business processing capability from a huge, complex, and highly related monolithic system. And second is how to decide the number of microservices. That will affect the quality of the system, and finding a suitable microservice scale is also an important process. There has been many research in this topic, such as methods based on functional symmetry similarity, methods based on the business process, methods based on the system security and scalability. Both schemes of microservice identification are effective from specific view of point, but do not consider the characteristic of database access. Because the database per service pattern is important in the microservice field, this study proposed a new way and an assistant tool to identify microservices based on the database access records. And our purpose is to migrate a monolithic application of the web front-end and back-end separation architecture to the microservice architecture. Each microservice should have logical business processing capabilities in different areas, so each microservice is more suitable to have an independent database, which also means that the service only focuses on the business work of a specific type of data. Our research team's approach is different from the existing research. We propose a set of a microservice migration method based on a database access analysis. And here is our background knowledge. We will use the aspect-oriented programming, that is AOP. That has 4 items. Aspect, modularization of concerns across multiple categories, include point card and advice. Join point, a point in program execution, such as method execution or exception handling. Advice, the behavior that aspect take at a particular join point, which advice has different types, such as around, before, and after. And a point card, a predicate expression that matches join point. Advice is associated with a point card expression and runs at any join point that matches the point card, such as executing a method with a specific name. And we also use the database. For database selection, the base database depends on how the organization intends to use the data, including the type of data stored, which affects how efficiently the database can be used. And this paper is to analyze the access of the relational database. And our research is based on the Spring Boot framework. The main design concept of a Spring Boot is to simplify the configuration to reduce the complexity of the construction and development of Spring applications. Spring Boot applications are generally divided into 3 layers: control layers, service layers, and repository layers. Control layer provides an API service endpoint externally, responsible for receiving front-end requests. It also adds service to process business logic and finally return response data. And the repository layer, as a data layer, it acts as a medium for communicating with the database and will be called by the service. And now let's discuss the proposed Miata approach. Miata is the microservice identification using the analysis for database access. First, let's see our functional requirement analysis. When monitoring whether all service requests in the application have access to a database or not, we found that only reading the service request time and method cannot help the clustering. So we decided to build a tool to deal with the above problems. We analyzed the need to be achieved, include the following 3 points. 1. By monitoring the access to a database, a record of the service endpoint accessing the database is generated. 2. Collecting the data that all service endpoint access to a database and find out the similarity between service endpoint based on the access characteristics. And 3. Through hierarchical clustering analysis, each service endpoint is classified, and then the most appropriate cluster size is found to suggest the suitable microservice segmentation method. And our operational concept is first, a user create a data table in 2 data formats in order to record the data of a request. And then the user add the code of the metadata, annotations, and aspect into the application. After that, a user modify the point card expression defined by the join point in the cross aspect to match the package name of a repository layer in the application. And then the user add metadata annotations to service endpoint that need to be monitored. And in the end, after starting the application, users can call the service endpoint. When a service endpoint request is successful, the request data will be recorded into a database. There are our applied technologies. First is based on the Java Spring Boot framework, and we'll use Spring AOP technology to dynamically monitor the behavior of the service endpoint. The core concept is to strengthen the business functions of the original target object without modifying the core of the original target object. And we also use the Java reflection technology. And here let's talk about the annotation and aspect design. Annotation is the users can mark this annotation on each service endpoint of a controller layer in the application. And a aspect is a method to detect whether a request operates the repository layer in the application. And we can see this picture. This is the annotations example. You can see this function is a request mapping function, and we can add this side of metadata here to monitor this function. And after that, let's see our process of migrating monoliths to microservice. It has 5 steps, and I will talk about each step in detail later. Step 1 is collecting data access record view AOP. Step 2 is logging links between service endpoint and corresponding data tables. Step 3 is analyzing the strength of relationship between server endpoint and data tables. Step 4 is analyzing the strength of relationship among service endpoint. And step 5 is generating microservice clustering candidates. In step 1, we will connect to a database location in the application, obtain the number of data tables in the database, and give each data table the position of the corresponding score vector. In step 2, once the controller layer API is called, which type is get or post method, a service request is generated, and we collect the service request data as a service request log. And it has 4 items: request time, request method, request URL, and a data body. And if a request uses the repository layer to communicate with database, that is the database access. And we also collect this database access data as a database access log. It has 5 items: ID, entity, table name, request time, and method. We collect all service request log and database access log data in the database. Then we found the corresponding database access log data for a request URL parameter in each service request log. We try to find out the relationship between the service endpoint and the data table. In step 3, we calculate method parameter in the database SS_log data format corresponding to the method of accessing the data table in this table and give the corresponding score. Like the get method, we will give it score 1, and the put method, we will give it score 3. And in step 4, each service endpoint corresponds to a score vector. We'll use cosine similarity to calculate the strength of a relationship between each service endpoint. And this is the formula of the cosine similarity. We then use the convention module to convert the degree of relevance between the service endpoint into distance with a value range of 0 to 1. If a value closer to 0 indicates that a relatively large number of similar data tables are accessed by the two service endpoints, while a value closer to 1 indicates that a relatively small number of these similar data tables are accessed. In the final step, we first output the distance between each service endpoint as a CSV file, and then there will be n multiply n values in the file, where n is the number of the service endpoints, so that we can use the various hierarchical clustering method for analysis. The service endpoint that access similar data are grouped into the same group, which means that the service endpoint in the group has a high degree of similarity. And here is our experiment and cases. Let's see our experimental design first. We will collect the existing project on GitHub and microservice migration case in other papers to simulate and collect requested data. There are 8 projects we collect. They have one project for 1 to 10 service endpoint, 4 projects to 11 to 20 service endpoint, 2 projects to 21 to 30 service endpoint, and 1 project to 41 to 50 service endpoint. And our experimental setup is, first, each project creates its own database and create its own data table in a data format. And 2, we set the ratio of service endpoint reading, adding or modifying database to 10 to 1, which will be fine-tuned through the random numbers. And 3, the service endpoint of each project are divided into 2 categories. One is the request main is get, and the main action is reading. And the other is the request main is post and put, and the main action are adding and modifying. And after collecting the data of the above simulation, the hierarchical clustering analysis can be carried out through the microservice migration method proposed by us. In our clustering evaluation criteria, here we use the address range index. We will calculate the ARI score of the market service endpoint and clustering results by address range index as a basis for our selection of the best clustering method and parameter value setting. But how to determine the clustering parameters? Because there are 4 clustering methods: complete, average, weighted, and central linked, and 9 parameter settings from 0.1 to 0.9. Output 36 cluster results. We plan to perform clustering based on the parameter settings of the top 3 ARI scores and recommend the clustering result to the users. Because the highest score has the same score of the 2 parameter settings, and the third highest score has the same score for the 7 parameter setting, we include these 9 parameter settings as the basis for recommending the microservice cutting method. And let's see our case and analysis. First is the case 1, plan approval. This is the let's see our data collection, and this is the process of the plan approval. We can see in this picture, the rounding rectangular indicate business process, and the files above indicate that the corresponding data object to be processed. The hollow arrows indicate that a given business process only read from the data table. The solid arrows indicate that a given business process involves operations to be added to the data table. Each business process is regarded as a service endpoint. And about determining the clustering parameters, this table lists the clustering method and parameter setting that earn the highest ARI score in case 1. And this table lists the clustering method and parameter values that were consistent with those trained using the 8 projects. And let's see our experiment result analysis. The two most recommended settings of clustering method and parameters that achieve the highest ARI scores did not achieve the best clustering effect in the brain approval case. But the best clustering effect was achieved using the clustering method and parameter settings that earn the third highest ARI score. We observe the clustering result generated using these settings. The best result is 4 clusters, and we call it option A. And the next best result is 5 clusters, and we call it operation B. The operation A and operation B's difference is that the sign order has its own group. And in the original paper, the service endpoints are only divided into 3 groups. From the viewpoint of the database access, it is accepted that business process which with access to the same data object are regarded as similar and are more likely to be grouped in the same group. So different from the operation C, we group evaluate quality and evaluate budget to the same group because they access the same data object. Besides, it's more suitable to move the AD plan and the provide plan process to form a new group. Because these two processes have both the writing data object plan and then the reading data object EST. Although the Miata recommendation setting cannot recommend the best clustering identifier manually, it can still recommend a more suitable clustering than the method proposed in the original paper. And the experiment results for COCOMI are very similar to the first experiment. Miata can recommend good service clustering that are more appropriate than the clustering of the original paper. And about how to apply a Miata, there are 2 ways. If the organization has no sufficient data on project, the user can apply our default recommended setting to produce Miata recommended service. But if the organization has multiple historical projects in the same domain, the users can first select multiple representative projects for use as a training data, and then conduct an AI analysis based on the result of applying the Miata method to these projects. And final is our conclusions. This paper introduced a microservice identification scheme based on database access. The proposed Miata system records historical data pertaining to database access requests to facilitate the selection of clustering method and corresponding parameters. Clusters of service endpoints can be used as a basis for the construction and microservice. In experiment on 2 real-world cases, Miata proved highly effective in the formulation of a microservice. And in the future, the purpose will be applied to a wider range of applications. And we also plan to extend support for the Miata tool, include other languages and platforms. Thank you.